Okay, so especially after spending a couple of years in San Diego, I've been obsessing for quite a while about the following two questions. So one is, what is the connection? Oh man, let's see. Let's try to. There we go. What's the connection between FPT algorithms or parameterized algorithms and exact algorithms? This is, let's say, call it question one. So in particular, can you use tools and techniques from one field to improve algorithms in the other? Are there any very direct connections where you can take algorithms from one of them and just directly apply them in the other? And the second question is, in exact algorithms, why are algorithms for satisfiability so different from algorithms for basically everything else? So basically, if you look at the algorithms for satisfiability and you compare them with, let's say, subset optimization problems, and I'm going to say here other subset optimization problems, then the algorithms look pretty different. And the reason I say other subset optimization problems is that satisfiability is actually a subset optimization problem. So what do I mean by a subset optimization problem here? Your input, say a graph or formula or something like that, defines some hidden family. And what you want to do is to just find one set in the family. So you have some universe of size m, so you have some input. It defines some universe of some size m and some family implicitly over the universe, and your goal is simply to find one set in the family, where you have oracle access to the family, being like, is this set in the family or not? Okay. So simple example, C-sat. I'm using neither K-sat nor D-sat for reasons that hopefully will become apparent during the talk. So this is so here, of course, input is a formula phi in C, C, and F. So all clauses have size at mod C. And the question is there an assignment that satisfies the formula? All right. How is this a subset problem? Well, the universe is the set of variables, right? And the family contains of all sets of variables such that setting them to true and everyone else to false satisfies the formula, right? Easy enough. All right, another one would be C heating set. So here, input is a family. Let's call it containing the sets S1, S2, Sm over some universe U, and you're asked, and also an integer k, and you're asked, does there exist a subset of the universe of size at most k that intersects all of the sets in the family? Right? And if this is C hitting set, then all of the sets have size at most C. Okay? How is that a subset problem? Well, your solutions or sets in the family are the sets of size at most k that intersect everyone in the input family. So again, there is some hidden implicit family that's implicitly defined by the input instance, and you ask, is this family non-empty or not? That's all you're doing. Okay. So now that we have set the stage and then asked the questions, defined subset problems, everything is nice and clean so far. Let's look at one already known, very concrete connection between FPT algorithms and exact algorithms. So in FPT algorithms, a question that is often asked is, can I find a solution of size at most k? right? So I give you some universe, and can I find a set in this implicit family of size at most k, and you want to measure your running time now not in terms of n, but in terms of this k. Fine. So in the parameterized version of CSAT, I would ask find satisfying assignment of weight at most k. So with at most k ones. Right. All right. So what about the connection between FPT and exact algorithms? So this is well known. I think this is folklore. So if my problem is solvable, if this is a subset problem, if it's solvable in time c to the k, then when I get an instance of size n, I can guess the size k of the solution. And for every value of k between 1 and n, I can do whatever is fastest out of running this algorithm and doing brute force. So then my runtime in terms of n is at most the maximum, because k is given to me by the devil, of the minimum of c to the k and n choose k. Okay. And notice that n choose k is better than 2 to the n, as long as k is bounded away from n over 2. Right? So if k is slightly less than n over 2, then you're doing better than 2 to the n. And c to the k, so if I look at k over 2, then 4 to the k over 2, that's 2 to the n, right? But if c is less than 4, then you're beating 2 to the n. Okay? So for c less than 4, you can beat 2 to the n. But this is somehow unsatisfactory, right? I mean, what about algorithms that run in time 10 to the n, or algorithms that run 10 to the k, or algorithms that run in time 4 to the k? Can you get anything from them? So one simple example of applying this algorithm is for the satisfiability problem. Suppose I want to give you an algorithm for 3SAT, so all clauses have size at most 3, and I want to find a satisfying assignment with at most k ones. There's a simple algorithm with running time 3 to the k, right? Because you pick up a clause that hasn't been satisfied yet. Oh, you need to flip one of the variables. Okay, you guess which one of the 3 variables to flip. So you branch in 3 ways, and in each of the directions you're going towards your solution. So after a depth k in your recursion tree, you would have reached your solution if there was one. So you can do this quite easily by local search in time 3 to the k. And then you ask yourself, okay, well, what does that give you here? Well, this gives you the stunning algorithm for 3SAT with running time 1.95 to the power n, which of course is much, much worse than everything else that's out there. Okay, so hopefully I've convinced you that, okay, this connection exists, but it's rather unsatisfactory. So you really want to do something better over here. Okay. So now we digress, or rather we end with this digression and then talk about the second question. And this is, why are SAT algorithms so different from algorithms for other problems? So what do the algorithms, the best algorithms for SAT look like, and what do the algorithms for the other problems look like? For SAT, there are basically 2 prevalent techniques. One is picking a random solution and then doing local search around it. And another one is random decision plus inference. So what do I mean by that? you pick a random variable, you randomly set its value. You pick another random variable, you randomly set its value. And then if at any point you have some variables so you know what their value should be, well, you set them to that. Okay? So this is the random decision plus inference paradigm, and then you have random sampling and local search paradigm, which I'm going to talk about mostly. So this is what I'm going to spend my time talking about. With respect to like basically everything else, with of course quite a few notable exceptions, the paradigm people use is branching. So what do I mean by branching? You pick up some element in your universe and you spend a lot of effort figuring out how to pick that element in a smart way, and then you decide either it goes into your solution or it doesn't. And then you measure your running time in terms of what happens. And somehow, for SAT algorithms, branching is what started out also to be giving the best algorithms, but it's a sort of quickly people figured out how to do other things. Whereas here, for everything else, D-hitting set, for example, branching is still the champion. So, before trying to understand how we can transfer some of the techniques from here over here, I want to talk a little bit about these kind of algorithms, because they're pretty cool. So I'll talk about an algorithm of Schoenig, building on algorithm of Papadimitriou, who gave an algorithm for KSAT using the following two ideas. So these ideas are sort of implicitly hidden inside of the paper. They're just below the surface, and then they were made explicit later by Danzig et al. But the first one of these ideas is the following. So for SAT, if we can do local search in time c to the power, let's say, L, okay, where c is some constant, then we can solve the problem in time 2 minus 2 over c plus 1 to the power n. Okay? So, for example, if you could do local search, I'll explain to you what I mean by local search. Okay? If you can do local search in time 2 to the L, then you can solve the problem in time 2 minus 2 over 2/3. Yes? So 4/3. Which is exactly what the running time of Schoenig's algorithm is, like 1.3333 to the n. Okay, so first, what is local search? What does Schoenig's algorithm do? So the local search problem is quite simple. So I give you as input the formula phi, still in CCNF, and then it's, I mean, I'm using the same constant for CCNF and the running time, and then that's not really a coincidence. But, okay, so I input as a formula phi, an assignment, let's say, call it sigma, and the question is, and an integer L, and the question is, does there exist a satisfying assignment, sigma prime, such that the distance from sigma to sigma prime is at most L? So the question is, if I give you an assignment that isn't satisfying yet, can I flip at most L of the variables from true to false or false to true, right? And satisfy the formula. Yes? And I claim that this problem does have an easy C to the L algorithm. I've already told it to you, right? As long as there is a clause that isn't satisfied, you guess which one of the variables you should flip, and then you do that. Right? So you branch into C ways, the depth of your recurrence is at most L, so you have C to the L leaves happy, happy. Okay, So what does this give you? Well, it gives you an algorithm with running time 2 minus 2 over 3 plus 1, so 4 to the power n. Right? Okay, so this is what Schoening does number 1. And then what Schoening does number 2, really cool idea, is that you don't really have to do the local search problem. It is sufficient to do permissive local search problem. Okay? So what is that? So just as before, input is phi and sigma and L. Your task now isn't to find a satisfying assignment of distance at most L. But your task is the following. If there exists a satisfying assignment sigma prime such that distance from sigma to sigma prime is at most L, then output some satisfying assignment. Okay? So if there is a satisfying assignment in the ball you're looking for, then output some satisfying assignment. And what Schoening showed was that this guy can actually be done in time 2 to the L, right? Giving the algorithm for SAT with running time 1.33 for 3 SAT with running time 1.333 for your favorite number of 3s. Okay. All right. So how does this reduction from local search to solving actually work? What you do is, based on the universe size m, you pick some L. So you pick an L that is based solely on the size of the universe and the running time of your local search algorithm, but your local search algorithm isn't dependent on the input, right? So you fix the local search algorithm and get, based on the size of the input, you fix L. Then you pick a random assignment. Fine. And then you run the permissive local search algorithm with that value of L as the parameter. So you have some success probability of ending up close to your solution, and then it takes some time to actually find that solution. And of course, the bigger L you pick, the better success probability you have of being close, and the more time you take searching the ball. And there is a clever way of picking L so that you get this running time. Okay. So what is exceptionally cool about this reduction from local search to solving? Well, it has nothing to do with SAT. This reduction of picking a random assignment and doing local search around it has nothing to do with SAT whatsoever. So, if you can do local search for any subset problem, then in time c to the L, then you can also solve it in time 2 minus 2 over c plus 1 to the m. Yay. Okay? Now, what do we mean by local search for the subset problem? Let me... So, input is some subset X of your universe, again, integer L, and your question is, does there exist a set S of the universe such that the size of S is at most L, such that if I take the symmetric difference of S and X, then that is a solution. Right? So if I pick up at most k elements of the universe. If they were in the solution, I take them out. If they were not in the solution, I put them in. And I ask, can I get the solution by doing that? All right, if I can do local search in this time, I can solve my problem in that time. Okay, we showed that you can do this for SAT. Now let's do it for the hitting set. Okay, so let's remember, what is the solution for the hitting set? So it is such that, so X is a solution. This means that the size of X is at most k. And for all sets Si in my input, the intersection of Si in X is non-empty. All right, so we have a simple local search algorithm for C set. Let's just use that for local search on the hitting set. Okay, as long as there is a set that hasn't gotten an element yet, some element has to be put in to your hitting set. Okay, let's do that. Fine, well, everything is great. You're still branching at time c to the k. But everything is a hitting set, right? Picking the entire universe is a hitting set. But it's too big. It doesn't satisfy this guy. Right? And now the question is, well, how can I start removing elements from my solution while keeping it a solution? And how fast can I do that? And you think about it, and you think about it, and you don't find an efficient solution. And the bad news is that you won't find an efficient solution, because this problem for the hitting set is actually W1 hard. Okay? So you just won't be able to do it, even for C equal to 2. So this for 2 hitting set, this is W1. Big sad face. Okay, so what can we do about that? Well, where were we having trouble in our local search? When we had to add elements to our solution, we were doing great. Right? When we had to remove elements from our solution, we were in deep trouble. So let's just make a local search where you can't remove things from your solution. So in particular, let's do the random sampling step of, like the randomized algorithm of Schrödinger, where you pick some initial seed and you do local search from it, but you make life easier for the local search algorithm by only being allowed to move upwards at the cost of decreasing your success probability in the first step, right? So you might have to change the size of the balls you're looking in. Okay, so now we were going to define a different problem. Okay, let's call this the extension problem, right? So it's basically the same as this, except that you're only allowed to add elements. So input is some set X and some L, and the question is, does there exist some set S now that isn't in your set X, such that the size of S is at most L, and X union S is a solution. Right. And now notice that for the hitting set, we do have, or C hitting set, has a C to the L algorithm for this problem, right? Because we did what I've told you several times now, as long as there is a set that isn't happy yet, there are only C ways to make it happy. Okay, so this works. What is our algorithm? Let me write it down. So
C in this case?
What?
What is C in this case?
So if it's 3 hitting set, so hitting with sets of size 3, then the local search algorithm is 3 to the L. If it is 5 hitting set, it's 5 to the L.
Size of the set. Size of the set.
Yes. Okay. So what does the algorithm do? Based on n and k, pick some integer t less than or equal to k. Okay. Sample a set x from the universe of size t uniformly at random. And now I want to do local search upwards from my set x. And now I actually know that if I picked t, I know that I will have to add k minus t elements in order to get up to my solution. Yes? So do extension from x with L equals k minus t, because that is how many elements I should add in order to get my solution. Okay? This is the algorithm. Okay? So when do I succeed? I succeed if now I have a solution, and when I pick this set, that set is actually a subset of my solution. Okay? So let's see. Yeah, this is. So let's look at one round of this algorithm. What is its running time and what is its success probability? So the running time of this guy well, it's just c to the power k minus t, right? Sampling is polynomial time. What is the success probability? Well, I have n choose t ways to pick a set from the universe. And if I have a solution of size k, then there are k choose t ways to pick a set of size t from the universe. Okay, fantastic. So my running time, now if I want to boost the success probability to constant, I have to run it this many times, right? 1 over success probability. So for constant success probability, my running time is going to be, let's see, let's do it here. Let's see, can everyone see what I write here? Okay, fine. So my running time is going to be n choose, let me put it a little bit closer. N choose t over k choose t times c to the k minus t. Yeah? Okay. Now, given k, we can compute this value for every t, right? So we can pick t so that this is minimized. So our running time is the minimum over k less than or equal to t. T less than or equal to k. Right? Because we have to sample a set that's smaller than our solution. But the size of the solution is, of course, given to us by the devil. So this is the max over k less than or equal to n. Yes? So this is the running time of our algorithm. Okay? And after about 2 pages of high school calculus, you can show that this is at most 2 minus 1 over c to the power n. Okay. So in particular, for 3-hitting set, we just gave an algorithm with running times of 3-hitting set. We just gave an algorithm with running time 1 minus 1 over 3 to the power n, 1.666 for the favorite number of 6. What?
2 minus 1 over 3.
2 minus 1.
The good Dimitri.
What? Oh, thank you. Okay. There we go. That would be exceptional. I mean, I heard graph isomorphism was a quasi-polynomial. Yeah, exactly. Okay. So, all right. So, here's another interesting thing. Let's look at the extension problem. Let's look at the extension problem for d-hitting set. So I give you some family, and I give you a set initially that I have to start from. I have to extend my solution by adding at most L guys. Okay? But notice that extending the solution in the hitting set instance quickly reducing to finding a solution of size at most L. Because for every vertex in S, or for every element that I know is in my hitting set anyway, all of the sets that contain him are hit. So you just remove him, and you remove all of the sets that contain him, right? So the extension problem prettily reduces to solving, right? So extension just reduces to find solution of size at most L. Well, now let's call it K, right? Not K. Yeah, okay. And this is what parameterized algorithms is all about, right? So for 3-hitting set, there is an algorithm with running time. So 3-hitting set, there is an algorithm with running time 2 to the 0, 7 something, 55 I think, to the K, right? So this immediately gives you a better algorithm here, 2 minus 1 over 2 to the 0, 7, 55, and so on. And this gives you an algorithm like something like 1 to the 53 to the n, beating what is there already.
No, this is not. K is maximized. Yes, K is maximized. So why?
I mean, L, sorry. I mean, think of it like this. So does this make it easier? Yes?
Is there a reason why you want to take L equal to K minus T and you don't want to try other values of L?
Here? Okay. Yes, because I picked T, right? And now I'm looking. So think of it like this. I'm looking for a solution of size K, right? And I need to try this. If I'm looking for a solution for size K, I need to try every possible value of K. Unless K is given to me as input. In the case of d-hitting set, K is actually given to me as input. I'm looking for a solution of size K, right? Then I'm going to pick a subset of size T, uniformly at random, and try to extend it. Well, if I have a subset of size T, and I'm trying to extend it to a set of size K, I better add K minus T elements.
I see.
Yeah. All right. So where were we? We were saying that, and this reduction here holds for a bunch of problems. Right? It holds for most things you like. So for most things you like that are subset problems, C to the K algorithms immediately give you 2 minus 1 over C to the N algorithms. Yay! Now we're happy. This is much cooler. And I won't really go into saying how you prove this, but let me convince you that any C to the K algorithm, or like C to the algorithm actually beats 2 to the N, right? In the previous trade-off, you needed something better than 4 to the K to beat 2 to the N. Now let me convince you that anything beats, so any c to the k actually beats 2 to the n. So suppose I give you as input n and k, right? So and I'm looking for a solution of size k. Then my running time is going to be n choose k if I pick a set and just try all possibilities. Okay, here is a ridiculous algorithm for trying all sets of size k. Pick a random set of size k and see if it is a solution or not. Repeat, right? Now, the success probability of picking a random set, random, is 1 over n choose k, right? Because if there is one solution and you pick one at random, that's the probability you pick it. Okay? Now, let's look at a different way of formulating the exact same thing. All right. When I pick my first element, what's the probability that that is a subset of the solution? Well, it's k over n. So it's like 1 over n choose k, which happens to be equal to k over n. Then I pick another element. My probability is k minus 1, n minus 1. I pick another element, and so on. And when I pick the tth element, my probability is n minus t by k minus t. And in the very end, my probability is k minus 1, also known as 1, divided by n minus k minus 1. What? Oh, thank you. I'm doing the same thing, right? Here we go. K minus t, n minus t. Thank you. All right. Okay. So this probability, if you think of k as being something like n half, this is quite good, right? This is something like about 1/2. This probability is pretty bad, right? This is 1 over n half, right? So this is something like 1 over n, right? And so your factors for success probability, you have n half of them, and they get worse and worse as you progress, right? At some point, the success probability drops, and so here this drops below 1 to the c, right? Because it starts out as good, and then it ends out really bad, and at some point it drops at 1 over c. And after that, it only keeps getting worse, right? So now, your success probability for these k minus t remaining elements, yes, is much worse than 1 over c to the k minus t. So it is much smarter to instead run the extension algorithm in time c to the k minus t. And this happens no matter what c is, right? Because 1 over n is less than 1 over c for any c. Yes?
When you go to the 1.5, didn't you apply the same method on a smaller thin set problem? Like you?
Yes.
Why can't you do it several times?
So what's happening is that you're sampling, and when you're sampling, your universe reduces, and at the same time your solution reduces. And what is happening is that the ratio of the universe size to the solution size changes.
So after one application is the best you can get?
Yes.
Interesting. Okay.
Okay. Yes. So I think it's quite easy from this to convince oneself that yes, indeed, for any c, you get something that's better than 2 to the n, right? However how much better is not obvious, and well, you differentiate this, do some maximum, do some minimum, and this is what you end up with. Honestly, I don't understand why. All right. What comments should I make? Well, some nice examples of applications to this, right? One we already saw, we got the best algorithm for D-hitting set, right? So another application is, let's look at the interval deletion problem. So I want to delete as few vertices as possible to get an interval graph. So interval graph. A graph is an interval graph if you can represent it as an intersection of intervals. Yes. Okay. So clearly you can do it in time 2 to the n. This is naive. Then quite recently there was some hard work done by people in this room, among others, that got it down to 2 minus epsilon to the power n for epsilon being something like 1 over 10 to the power 20. Right? At the same time, there is a recent published algorithm for interval deletion with running time 8 to the power k. So can I find a solution of size k in time 8 power k? So what our theorem does, immediately, 1.875 to the power n. Quite noticeable bit, right? All right. Let's look at another example. Let's look at the min once sat problem. So this is the variant of the sat satisfiability problem, where I not only want to find the satisfying assignment, I want to find the satisfying assignment with a minimum number of ones in it. Right? So so of course the local search thing that we did runs in time c to the k even for that. Right? And now we're getting min 1 sat in time 2 minus 1 over c to the power n. So for 3 sat, it's again 1.66666 to the n for satisfying assignments with the minimum number of ones. So in the savings in the exponent, this is order of magnitude the same as for normal k-sat, right? And as far as I know, I don't know how well studied this problem actually is. The best thing I know is the naive algorithm that like picks a clause and says either this guy is true or this guy's false, that guy is true, and so on. This gives you savings 1 over 2 to the c, so much worse than savings 1 over c. Okay. So this is significant progress. Okay. Another problem before I move on with more technical things is feedback vertex set. So I give you as input a graph G and an integer k. So feedback vertex set. So input is a graph G, integer k, and the question is, can I delete at most k vertices such that G becomes acyclic? So this is for undirected graphs. And for a while it was even open whether this problem can be done better than time 2 to the n. And then there was some good progress. It went down from 2 to the n to something like 1.85 to the n, then to 1.75 to the n, then to 1.74 to the n, then to 1.73 to the n. Right?
A cyclic graph?
Yes, so a forest. So I have a graph G, integer k. Undirected, yes.
And remove the space.
Is a cyclic. Thank you.
Because I can interpret this in 2 ways.
There we go. All right. Okay. So this is the progress that's been happening for this paper, for this problem. However, we are very happy this has a very cool algorithm running time 3 to the k. Yes. So we get 1.6667 to the n. Yay. Okay. And there are a bunch of more examples. You can see look at the paper. These are some of the ones I'm most happy about. But before we conclude, let me say some more things, what we get out of it, and also a little bit about de-randomization. Okay. So, what is it we were really doing? We had some hidden family of solutions. Right? So we had some hidden family. And our analysis was that if you can do local search, so if local search in time c to the L, then I can find a solution in time 2 minus 1 over c to the n. Right? This is what we said. Okay. Now, how did that analysis look like? We picked up one set in the family, and we asked how much time will it take to find that set. Right? So in particular, if I instead could say something like this, if for any set x of size t, the number of k minus t extensions, right, the number of ways to extend that set to a solution by adding k minus t vertices, is at most c to the k minus t, then the number of solutions is actually at most 2 minus 1 over c to the n. Right? Just the same argument. I mean, I'm not going to repeat the argument. It is really the same one. You have some random process where you first pick a random subset of size t, and then out of all the extensions, pick one at random. And then you lower bound the probability for every set in your family of that set being the one you picked. Yes? Okay, and then it ends up being at most this many sets. So, for example, for 3 hitting set, what we actually end up doing is enumerating extensions of my sets that are minimal hitting sets. Yes? So, for example, this implies that the number of minimal 3 hitting sets is at most 2 minus 1/3 to the power n. So this is like 1.6667 to the n. 7 to the n. Thank you. Okay, there we go. Okay. So for example, here is some nice facts. So in a tournament, this is this graph where between every pair of vertices there is an arc in one of the 2 directions. And Moon showed in 71 that the number of minimal feedback vertex sets in a tournament, or maximum induced acyclic subtournaments, is something like 1.71 to the power n. Then Gaspers and Nick later improved this to 1.67 to the n, and now our result just immediately gets it from 1.67 to 1.6667. Some more sixes. Just in one shot. I think this is quite cool. Another thing is that this also applies to minimal satisfying assignments. You can enumerate. So this is a crazy thing, right? Like checking whether a given assignment is a minimal satisfying assignment, so whether you can take some variables and flip them from true to false and still satisfy the formula. This is NP-complete. Right? But so we can't actually even enumerate all of them. But we can enumerate a superset of them and say that the number of minimal satisfying assignments is at most this. Which is quite nice. What else should I say? Let's see, how much time do I have? I have a few more minutes. Okay. So this algorithm is sort of inherently randomized, right? We picked a random subset, and we tried doing local search up from it. And you don't know anything about your solution, so how can you de-randomize it? Well, you do know one thing about about your solution. You know its size. Right? You know that this is a solution of size k. So let's figure out how to use that to de-randomize it, because we actually can do that. So recall that my success probability was k choose t over n choose t, and my running time was c to the k minus t. Okay, so based on k, I'm picking a number t, and I'm sampling sets of size t, uniformly at random, right? And I am succeeding if I picked a set that was subset of my solution. And I have to repeat my trial inverse of this many times. Okay, what if I constructed the following thing? So what if I construct a family F containing sets x1, x2, xr, so all of my xi's have the same size t, and they have the following property, that for any set S such that the size of S is equal to k, there is some guy in my family who is a subset of them. Yes? So there exists xi in the family such that xi is a subset of S. Then, if I had a good construction of such a family, then instead of picking things at random, I could just run the local search from every set in the family, and my running time would be the size of the family times c to the k minus t. And we do construct a family of size exactly this, of course, with some sub-exponential overhead, but that doesn't really matter. Okay, and the cool thing is that this also gives us a deterministic algorithm to enumerate all of the objects that we could count the number of. But this is exponential space because you need to keep track of who you have already output and remove duplicates, if you care about not having duplicates. Yeah, I won't say much about the de-randomization, so let me conclude with a little bit of philosophical remarks. All right. So, c to the k was enough to beat to beat 2 to the n, right? Because it eventually beats n choose k, right? So in particular, also, if I do something slightly better than n choose k at the cost of any c to the k, that still beats n choose k. So like c to the k times n choose k to the power 0.99 does eventually beat n choose k when k is small enough compared to n. And I think this gives hope for using this sort of approach for problems that don't have single exponential time algorithms. For example, directed feedback vertex set, right, has an FPT algorithm with running time k to the k. So for k being something like n over log n, that algorithm is faster than brute force, right? But if you could make that algorithm run in time 100 to the k times square root of n choose k, right, then you would actually could use that to beat 2 to the n. I mean, there is already an algorithm better than 2 to the n. It runs in 1.9977 to the n by Rasgon. But I have some hopes that maybe something like this could actually beat it, okay, without having to get a single exponential algorithm for DFES, because that's a major open problem. Another thing is that some people here are interested in algorithms even with running time 2 to the n minus 1 over g of n, so when you have savings that depend on your input size, right? And notice that our approach basically gives you savings like that starting from any FPT algorithm. Right? Of course, depending on your dependence on k, this becomes worse and worse. It would be interesting, and because these things sometimes are useful for proving circuit lower bounds, I would be very happy to see someone prove a circuit lower bound starting from an FPT algorithm. Let's see. So what we are doing right now is we really have a two-step process. You pick a random set, and then you run a local search algorithm, right? Picking a random set is sort of I mean, it's also a branching process, right? You just pick a random vertex, or pick another random vertex, and so on. And many of these local search algorithms are also branching algorithms. And it makes sense that somehow if you interleave the random picking and the local search steps, you might be able to get something better. So in fact, with some tinkering here and there, for many of the problems we consider, we could get something better, but it required a lot of tinkering, and we only got like fifth decimal improvements. Meh, right? So in particular, for example, for the number of tournament feedback vertex sets, 1.66667 to the n is not the answer. The answer is smaller than that, but the gap between what we got and this is so small that it's not even worth mentioning. Yep. So one last one is, well, we used monotone local search to get exact algorithms. I just wonder whether there are any interesting exact algorithms problems for whom the normal local search problem is easy, other than just satisfiability. It would be fun to get some good exact algorithms based on that as well. Okay, thanks.
Any comments or questions?
If C goes up, like in the user, there is no hope. More or less you're saying, right?
What?
For the general side.
Oh.
C is not constant.
So an interesting thing, I mean, okay, our approach doesn't do anything. I mean, okay, so our approach does the following. If you can do k-sat in time n choose, I mean, okay, if you can do c-sat and find a solution of size k better than n choose k, for any linear, so basically instead of looking at, I mean, instead of beating 2 to the n, you can beat n choose k when you're looking for small solutions. But we still don't know how to do that, and like the pessimistic view would be that you can't do that under strong ATH.
I was wondering, for this denormalization, can you use this 0, t lopsided universal sets?
No. It's. I mean, the construction has some similarities, but it is not the same.
Are you getting any new lower bounds, like proving hardness, W hardness for some problem that from this construction that was not known before?
We haven't looked into it.
This is a philosophical question that your works seem to obsolete previous hard work on improving exact algorithms. So where all those ideas go? So are they useless or misguided, or maybe if those ideas are reintroduced on top of your technique, then something can be improved?
So this is what I said. Basically, I mean, if those, so typically, if you reintroduced those ideas on top of our technique and did some tinkering, then you could get really, really tiny improvements. But I think that is mostly because we haven't figured out the right way of combining existing things with our thing yet. And I think this is a very good question.
The question goes back to a conversation we had in Corsica a while back. And the question is, see, this runs on, you have k and you're running it up through n. And you're better to do the FPT for a while. And then eventually it's better to do n choose k. Do we know any examples where in some intermediate range, like you basically have two phases and you're worrying about when to move the boundary? Do we know any examples where as k runs up through n, you have 3 different phases, if you know what I mean, the 3 different algorithms.
So if the running time of the local search algorithm doesn't only depend on the number of things you're adding, but also the size of the set you sampled, it has to depend on it in a very good way for this to happen. Then I think pretty much that is what happens, but I'm not sure. Like, we did some analysis on that, but I mean, okay, now I'm just guessing.
So what is the title of the paper we should read here?
Fast exact algorithms based on monotone local search. It will eventually make its way onto archive.
Oh, it's not up.
It's not up yet.
Thanks again.